Or if you just want to see the mesh alone, choose solid color and choose wireframe. Then you have the mesh here, and if you tilt it, you will see, yes, this is a two-dimensional case. OpenFOAM is always three-dimensional, so you need then one cell thickness in the third direction. That's sort of unavoidable. Looking at the pressure, yes, we get, as we expect, low pressure in this corner, high pressure in this corner. So this is the square cavity test case. Now this one is of course childish, stupid. Reynolds number is very low. So let's spice it up a little bit. Remove that one, and now I want to destroy all my result files. I want to destroy all these folders here. Not the first one, the 0. I want to keep that one. That's the initial stage. But these I want to destroy. You can do it graphically, but it's here possible to write remove minus R, but now you have to be careful. You write the names of all of those, but here I would remove all the folders starting with a 0 and a dot. And then the rest of the name I don't care, so there I just use a star. This one will remove everything starting with 0. But he won't destroy the first one, because it should start with a 0 dot, and the first one he doesn't have a dot even, he's just 0. So that one should destroy everything except the first one. So there I'm back to square one. Now start the editor, gedit. And then we start looking into the constant and the transport properties. There you have the viscosity. It's 1 over 100. Okay? That's the viscosity. What else do we need to find the Reynolds number? We need the size. Then we look into the mesh. So we open the pooling mesh and the block mesh dict file. The block mesh dict file, this one is a fairly easy setup. You start here by defining your corners in your domain. And for this square cavity, it's the simplest geometry possible. We only have one block, one square. So here the x, y, and z positions, so you see the x and y, they go from 0 to 1. The z position goes from 0 to 0.1. It's a two-dimensional case, so the z direction, as a convention, they say, should be 10% of your dimension here when you are doing a two-dimensional case. It's not that important actually, but they say 10%. This number is a little dangerous. Convert to meters. That means all these numbers here, all these distances in meters, will be multiplied with 0.1. So I don't have a square cavity of 1 by 1 meter. It's 10 by 10 centimeters due to this number. So I don't want that. I want him to be 1 by 1 meter. I changed that one to 1. Next, having defined your vortices, you construct what's called a block. And here I only have 8 corners, so I only have the options here to create one single block. How to create a block, we will look into it later. It's just a number of these different corners. But here you specify the number of cells inside the block. And here it says to be 20 by 20 by 1. And the simple grading, that is an easy way to stretch the mesh if you want it denser to one wall or the other wall. So leave it 1, 1, 1, no stretching, but I don't want 20, 20. I want, say, 100, 100 or something. So let's change him. 100 by 100. Further down in this mesh file, you now have the definition of the different faces that you have for your domain. So you invent names for them. A moving wall, fixed wall, front and back. These are names that you create. You can call them anything you like. Never use Norwegian letters. Never, ever. Very bad idea. So, and also no space or plus or minus inside here. Not allowed. But give them names, logical names. And here you now specify which corners will define this face, this plate. We'll come back to the logic later. What's important here is these names now has to be specified for the initial conditions and the boundary conditions. Where can we find those? Well, first of all, I save this file, and now I open the file in my Cavity 0 folder. In the 0 folder, you find now initial and boundary conditions for pressure and velocity. Starting with the velocity. The dimension, meters per second, and then you can also give him an initial field, a value throughout the entire domain if you like, but here everything is specified to be 0. The moving wall is a fixed value type with 1 meters per second in the x direction. Now I have enough information to calculate my Reynolds number. Viscosity was 1 over 100. Dimension was 1 meter. Velocity is 1 meter. Okay, my Reynolds number is 100. Reynolds number 100, that's for kids. So I go into the block mesh dict. No, I'd go into the transnet properties. This is the viscosity. I want a Reynolds number of 1000. So another 0 in here. Now I'll have a Reynolds number of 1000. Save this one. Let's have a more look into the U velocities. Not so exciting. The rest is the fixed wall. The 3 other walls, they're standing still. Then you have a no-slip condition, of course. Front and back, you just write empty. That's telling OpenFOAM, it's a 2-dimensional simulation. So you use the word empty. For the pressure, we really don't have to do anything. As you see, against a solid wall, whether he's moving or not, you use 0 gradient, Neumann condition for the pressure. Here, check the dimension for the pressure. No kilos. Meter square per second square. It's a very strange dimension for a pressure. But remember, for incompressible flows, this is the pressure divided by the density. Okay, now all these files should be saved and everything should be A-OK to run. Now I have to recreate the mesh. He still remembers the first mesh, 20 by 20 cells, so I have to run this block mesh again. Like this. So now number of cells, 10,000. 100 by 100, that makes sense. If you want to investigate your mesh, have you done something wrong? You can write a program called check mesh with big M. He will investigate this mesh a little more thoroughly, checking that everything is okay, and end up with mesh okay. If it's not okay, then you have done something wrong, or maybe you should adjust it a little bit. Here, it's a difference also with errors and warnings. It can give you a warning if you have a mesh, not 90 degree, but very, very stretched, sort of. That's also possible in this structure. So use check mesh if you're ever in doubt. Now I should be able to run. But, well, let's just try and see what happens. ICO foam. It starts to run at least. But let's freeze in. Control S. I want to see what's going on here. Yeah, well, actually, he looks okay. He's halfway, 2.5. The Current number is printed out here. On average 0.02, on maximum is 0.4, way below 1. So this looks okay. If you have a Current number bigger than 1 here, warning, smaller delta T. But this one he seems to be able of running through. The residuals should be small and they look quite okay. So Control Q, continue the simulation. And yeah, he has done so quite nicely. We have the same result folders as we had previously. So let's now check with Parafoam how they look. Clicking apply, choosing the velocity and click play. There you should have sort of a warning here. He started to develop some change were about to happen, but he definitely wasn't finished. If you rewind and play again, you see something is starting to happen here. So obviously 0.5 is too short time. You need to simulate longer. Remember, smaller Reynolds number, less viscosity. So the first case, that was honey or a very sticky fluid. So you get the steady state very fast. Here, it's much lower viscosity. It's going to take a long time to find the correct solution. So I write gedit. Again, open the system control dict file and tell him don't stop at 0.5. That is not long enough. I want to go all the way, say, to 5. That should be okay. Save that one. Now I can just run again. I could have here said start from latest time. Then he would have started from where he left off the last time, instead of starting from 0. But it doesn't take that long anyway, so I don't care. I start from 0 and run ICO-foam again. And then he has to run for a while before he finds the solution. Kjempelse?
Nei, de er ganske raske mine.
Det er 5 år gammel.
Jeg tror den er ganske treg. Den her er ganske treg.
Kjører du i Linux? Ja, det gjør du. Du har bytta på.
Ja.
Den der må være veldig gammel.
Ja, den er litt gammel.
Så da skulle du ikke kanskje ha tatt 100 ganger 100. Du kunne klart dem med 20 eller 30.
Det er ikke så imponerende.
Vi kan jo kalle det. I guess it's a slow one. Not that fast. Jeg har det tidligere også, men jeg må begynne med å
Kontoplass. Pause i prosessen eller pause bare avslutten?
Prosessen.
Vi ser prosessen, ja, ok. Så
Så hvis du, det kan du jo sjekke.
jeg trodde sånn tida hadde fått
Nei, du kan se det med Ctrl S der, og så åpner jeg et nytt vindu.
Og jeg med selvbruk.
Så tar du topp.
Ja.
Så vil du se her at man gjør egentlig ikke så veldig mye denne her prosessen. Men hvis du nå vekker den opp i bakgrunnen her, Ctrl Q, så dukker den opp med en gang.
Ja, ok.
Ja, så der ser du, åja, at du fryser hele greia og frigir hele CPU-en til andre siden. One thing I forgot to mention for the in the previous simulation when we run this daily case, that was a steady state code, and we have instructed him to use maximum 1,000 time steps, but he will stop automatically when he finds a steady state solution. On my computer he stopped at 760. This is a transient code. He will continue until the end of time that's specified, so that's a different logic behind it. A steady state code, he will just stop whenever he is satisfied. So now I have a lot of result folders, but now each of every one of these will now it should be correct. It should be the correct time development. So here, yes, it's possible now to create animations, see how the flow develops, and so on. Parafoam. Let's have a look. Clicking apply and choosing the velocity and click play. So now you should have the more correct time development of this flow. And clearly he's not really finished. If you look at just a couple of frames back, you can step backwards here, you can still see the changes between the latest folders. So you are not at steady state yet. You don't have it exactly, it's only visual, but at least you get an idea. Is this steady state or what? And now for the pressure. That's easy to see for you. Low pressure here, high pressure, and then I have a low pressure here somewhere in the center of this primary vortex that's now have started to form. If you want to look at the mesh, it's now 100 by 100 mesh, so clearly much more dense solution. Still only one cell thick in the set direction. If we zoom in here, in the top corner, it's sort of a problem for him in the upper left and right corners. It's a singular point. The top wall is moving with 1 meter per second. The side wall is standing still. So in the corner here, the velocity is not well defined at all. But I mean, he handles it decently, taking an average over this cell. In this menu for what to plot, you have sort of a double choice. The pressure and velocity, but also you have a pressure and velocity up here. Now if I choose the one up there instead, he has a different logic on displaying it. he will now display one constant value within one cell. So it's another way of thinking. So the other one will now be much smoother. He will interpolate the values much more nicely. So this one, it's, I can remove the edges here. When you have 100 by 100, you can hardly tell the difference. But now it's a little bit more crude, more block plotted. While the other one, he will interpolate as best as he can. OpenFOAM is a co-located mesh system, meaning velocities and pressure are located in the cell centers. So here he interpolates from center to center. Okay. I don't think I will go too far today because we have another lecture at 4 I have to be in charge of. But before we end today, I want to show you something that you can play around with yourself. Let's just exit this one and have a look at what is brought in with the OpenFOAM package. You have some documentation on OpenFOAM, not much, but a little bit. So you can click either on OpenFOAM, this one, or Places, Computer, one of these. Here, the computer, then he lists all the hardware he finds. So here's a file system, and also a subfolder or a sub-partition within this hard drive. CD drive, the Kingston Data Traveler, that's my USB stick. And on that he has his own file system. So if I double click on this one, you can, what is called, mount your local hard drive. That's nice if you want to have result files from OpenFOAM copied into your own hard drive on the computer. Yes, then you can just double click on him and he will be mounted. Just know what you're doing. There you can destroy the hard drive without any questions. So here I want to go into my file system. Now you are on the root level on your USB stick on the file system. So a lot of these folders is not for us to play around with. It's a default part of Linux. You will have your home folder that's inside here. All the users will be listed inside home. Your username is Ubuntu by default here. OpenFOAM is in the opt folder. Remember, that's where we found the tutorials. So you can address opt, OpenFOAM, and here you can play around with all different tutorials, and you have many of them with this package. What I want to see here is the documentation. That's what I wanted to show you. Documentation, and then A4 guides. You have two files. User guide and programmer's guide. User guide for children, programmer's guide for grown-ups. So we start with user guide. And he starts by saying a lot of GNU-free software, meaning you are not allowed to make money on this, meaning you can do whatever you want with it. And the tutorial, chapter 2, starts of course with the classical cavity test case, which we have played around with. So if you want, you can follow him step by step. Then you should download the tutorial once more. What you shouldn't do is what this tutorial recommends. As a first step, he copies all the tutorials into your run folder. I won't recommend it. You only have a limited amount of space on this USB stick anyway. So don't copy all of them. Take only the single tutorial case you are interested in. But here you can have a look at the mesh, you can have a look at contour plots, vector plots, streamline plots, So you can sort of follow the recipe here a little bit if you are interested in how this one is done. Changing the Reynolds number, we have done already actually. Then he has some other test cases. So we will play around with some of these next week. Here, then, a little interesting, some list of libraries that exists in OpenFOAM. So a little bit about compiling and a list of all the different programs. And you have many different programs. So again, we will have a look at this later on. The other file, Programmer's Guide. Go a little bit more in depth into the details here. It starts with tensor mathematics, nothing that we really need to worry about here. Discretization. So here is now I talk about how should you choose your solvers, the solution procedure, how should you, what discretization scheme should you choose, some information of the different options there in OpenFOAM. And then examples of use. So steady turbulent flow over a backward facing step, that's this BITS daily case we have just looked a little bit into. So a lot of different cases here as well. But that's sadly the only documentation that exists when it comes to OpenFOAM. When they started OpenFOAM, one of the authors, he wrote some documentation of OpenFOAM, a little bit in detail how it is discretized, how the schemes are implemented, how the programs is set up. And then he wanted to make money on the documentation. So every time somebody now tries to write some documentation on OpenFOAM and make it available, he will sue them. So it doesn't exist. So you don't have any detailed, well documentation on OpenFOAM. Sadly, no, we don't have. The source code is there. It's just to read it. That's not easy. That's C++. But the code is there. And everybody knows it, and a lot of people are then capable of writing good documentation, but they're not allowed to, sadly. So we miss actually a well documentation on this OpenFOAM.
But did that person sells good documentation then?
No.
If you want to pay for it?
No.
Oh, he did?
No.
You just want to block your
He's a very strange guy. I don't know why. So I mean, you find all sorts. So no, this is sort of all we have. If you are really interested in how it's done more in practice, if you need some theory background, I would recommend this numerical book by Versteeg, Control Volume, Finite Volume Method. That's more or less direct recipe how it's done. So that book, I think I've given it to you already in the reference folder in ISLearning. So you have it already. If you really need some documentation, the way to think about finite volume codes and how they are implemented. But for now, I would suggest play around inside the user guide. See if you can make it run. Yeah, the dam break, well, we can take that one, because that one is very funny. We have time to one more tutorial. So we start again. First thing you do, run. Stand in your run folder. Now we want to copy the, where did I put it? The square cavity, the dam break case. So we start again, cp minus r slash opt open foam tutorials.
Which
And-
solver you need?
This one, it's a multi-phase flow, so it's an interfoam.
Yeah.
So under tutorials, we go multi and then inter. And under inter, you have several, interdymfoam and interfoam. Interfoam is the one we are going to use. And then the case should be laminar. And we have the dam break. Space and a period. So there we have copied the dam break case into our folder. So we write change directory into dam break. But here we have multi-phase flow. So we have some additional step we have to do. If you how do we do this? Write gedit and then put an ampersand and at the end of the command. What happens then is he will execute the command starting this editor, but he will also give the control back to the command window. So now you can continue writing other commands. Without this ampersand, this window will be locked until you are finished with using the editor. But now you have both of them operative at the same time. So this ampersand, that's a nice one. Here I want to have a look into this 0 folder where we have velocity u. I have a strange pressure, rho gh. So here they are looking at sort of the static pressure from gravity has been removed, so has been subtracted for the pressure. And then I have something called alpha1.org. What the heck is that? Alpha1.org. Well, when you are dealing with multi-phase, you use an alpha to distinguish which phase are you into. Are you into liquid or gas? Now we are talking water and air as a case here. So alpha equals 1 is just liquid. Alpha equals 0 is just air. Alpha equals 1/2, 50% of each inside that cell. So you use alpha to play around with more than one phase at a time. But we have to give him an initial value. So here, for this setup, they have given us an original alpha 1. And the first thing you have to do is to make a copy of this original. So you write cp for copy, space, and then 0 slash this alpha1.org, copy from, and now we have to specify copy to, and it goes into the same 0 folder with the same name, except the last name. It's just called alpha1. So that one has to be executed first. And as you can see now in my editor, all of a sudden another file popped up. It's just a copy, so they should be identical. Let's have a look at this alpha1 file. This alpha1, he will now be sort of at the exact same form as the other one we had for pressure and velocity. The dimension is nothing, it's a non-dimensional value. Everything is given to be 0, that means air in this case. Boundary conditions. We have the left wall, the right wall, lower wall, just 0 gradient, fair enough. And then we have an atmosphere. That's interesting, atmosphere. There it can be in or out. We don't really care. And if it goes in, then he gets the value 0, meaning only free air comes in. If he goes out, then he will just disappear. And then In the Z direction, default faces, empty. So it's still a two-dimensional case. Now leave this window open. And we have now a program which will help us initially to distribute the different domains. What should be water, what should be air. It's called set fields. Large F. Fields. This is a program that will read information given from another initial file called setfields.dict, where you can specify which area should be water, which area should be air. And he will now overwrite this alpha1 file. You can see the effect when you run, oh yeah. Ah, my mistake. We have to create the mesh first, of course. Block mesh. Sorry. Block mesh has to be run first, of course. Not that big a case. 2,200 cells. So it's not so heavy. Now let's try again. Set fields. There, he has done it. And now go back to the editor. Now you see you get a warning here. This file has been changed. Do you want to reload it? Oh yes, I want to see what happened with it. And then you see what happened. He has now put in zeros and 1 in a long sequence. 2,200 and something of them, saying in which cell should the alpha be 0 and which cell should it be 1. So, of course, you don't want to do this by hand. That is why you have this set field script to do it. And you see the file is long, so this is going to take a long, boring time to sit here and punch everything. So now we have an initial state, we have a setup, and if you are curious, you just want to see how it looks before you start the simulation, you can do that. You can still write parafoam before you start the simulation. That's actually possible. Now, before I hit apply, I want to scroll down here and see the different options. What can I read? The default is only the velocity. Well, I definitely want to have a look at this alpha1 parameter. So I click on him and then apply. Okay, so this is the layout and wireframe. There you have the mesh. So you have solid walls and an open atmosphere, and then you have a sort of small dam or a block here, solid block. That's the initial state. Sorry, the geometry. And now if you choose the alpha1, there you see what happens. If you want the numbers, hit legend up here. So there you see alpha is set to be 1 inside here. So here you have water. The rest is air. So the problem, the physical problem would now be you have a dam here and of course a solid wall here. And now at t equals 0, this wall is destroyed. It's removed. So let the water start to fall. And here is your house. Now let's see what happens to it. Exit this one and start the simulation. And it's called interfoam, wasn't it? Yes. Inter large F foam. Shouldn't take too long. There, he was finished on my computer. He has created some result folders. So I start parafoam again.
again, remember to specify alpha 1. I want him definitely. And then apply, choosing alpha 1. And now you can click play and see what happens. So clearly you are going to get wet. Together with this tutorial, I found some information about this case, so you can play around with it if you like. What also you have been given information on there is how to run using more than one CPU, running this case in parallel. So that's also an option. We can have a look at it next week. Should be okay. Also here, how to create an animation. You can make a video out of the result files. It's fairly cool. Just for now, if you are curious, when you bought the computer, the salesman said that your machine, your PC, yes, I know it's very expensive, but it's a very good PC, so you have to pay a lot of money for it. He has 20 CPUs inside. Now you can check if the salesperson lied. You can write LS CPU. And there you get the list. How many CPUs do you have? On my computer I have 2. That's all. And if you have 1, okay, then you can't run in parallel. So I believe on a good computer you should have 4 or 8. Then the OpenFOAM will actually scale quite nicely. So with 4 or 8 CPUs, you can really speed up the simulation time a lot. That's actually a good option here. If you have 2 CPUs, you don't half the time, but you use say 60% of the time or something. So OpenFOAM is fairly okay when it comes to scaling. It will go a lot faster with more than 1 CPU. So it's a good program. Anybody got more than 4 CPUs here? No? You have? How many do you have on that one?
8.
You have 8?
Yeah.
Then it cost you a little bit. I guess. Yeah. Okay. I have to run to the my next lecture. If you want, you can please sit here and play around as long as you like, but I have to leave. Next week, I will say that we skip Tuesday morning. It's no point starting 8 o'clock in the morning, and then we have to leave by 10 anyway. So next Wednesday from 1, we can have another session here. I have some more cases I want to show you. I also have a part 2 of this paper that also includes how to change the code, how to make your own version of an OpenFOAM. But I mean, already now you know enough to get hold of one tutorial. Start playing around with it. Change the input file. See what happens. Make it crash. No problem. So start messing around. And if you destroy anything, no problem. Just remove it and make another copy from the tutorial folder. Just don't destroy the originals. But I have more memory pins here, so no problem. You can't really do anything wrong here. Any questions from you? Okay, then I have to run.
Jag tänkte göra det. Sen tog jag det och så kör jag ett semester. Så kör jag planer och jag ska faktiskt bara sticka och kanske det går fort. Snart blir det